Hey everyone, welcome to your Play Pause It for the week. We are going to be covering lesson 2.12, the very last lesson in Unit 2. So go ahead and grab your notes, have your OMHS Play Pause It graded assignment open, and we'll get started. I wanted to just make a mention that I'm using a new writing tab today. So bear with me. Hopefully it's all calibrated properly and we'll be able to do this well. There we go. Cool. So here's our first question for the day. We haven't done an SOL flashback in a long time because we've been doing those Be the Teacher sessions. So I wanted to bring these back. And these are going to be questions that you guys might actually see on the SOL. I pulled them from previous versions of the test and also some other sites that have SOL type questions. So it says, which represents this expression in simplest form? Excuse me. All right, so the first thing we're going to do is want to look at, let me grab my pen again, this tablet for the first time. Whenever you guys have an exponent here, on the outside of those parentheses, it means to multiply. So we're going to multiply -2 times 3. This is a great pen. This is just great. I was nervous. Look at that. All right, and we'll do the same thing with the denominator. So this -3 is going to everything that it's touching with those parentheses. So -4 times -3 is +12. There we go. Now we're going to keep reducing. There's kind of a few ways you can go from here. Just depends on what you see first, kind of how your brain processes the next step. I personally see these coefficients here, 15 over 3, and we know that reduces to 5, right? 3 goes into 15, 3 goes into 3 once, and 3 goes into 15 5 times. So we'll just take it a step at a time. That reduces to 5 over 1. Now again, here you have two options. I don't know about you guys, but I see this negative exponent and I'm like, we gotta make it positive. Remember, we don't like negative exponents. So to make them positive, you just put them either in the denominator or in the numerator. You kind of flip it. Remember, not really flip, but you move the negative part. So we're going to move this to the denominator. So we're going to end up with 5 over x to the 12 times x to the 6. When you move it to the denominator, it makes it positive. It's kind of like multiplying by the reciprocal. So again, you're not really flipping because the x to the 12th didn't go to the top. You're just moving the negative part. Okay, now remember here in the denominator, we have the same base. They're both x's. And when we're multiplying, what do we do to the exponents? We add them. So we're really going to have 5 over x to the 18. 12 plus 6 is 18. And that's it. We can't do anything else. All of our exponents are positive, and everything is reduced down as far as it will go. So here it is. The answer is D, 5 over x to the 18. Hopefully that brought back some memories of those different exponent rules. All right, so now we're just going to get into factoring. We're going to do a few more factoring examples, and then we're going to get to that very last part. So I know we've done a few different types of factoring, and the first step should always be, is there a GCF? And I wanted to show you guys a few where that is the case. So if you looked at, these are the same problems, so we're going to get rid of that one. If you looked at each three of these terms, we want to find or ask ourselves, is there a GCF of all three? Remember, they all have to have it in common. So we could do the cake method and write all the numbers here and take a look and see if there's a number that goes into all of them. I typically start with 2 and kind of say, oh, does 2 go into these? Well, we know 2 doesn't go into 3. So then let's try 3. Sure enough, 3 goes into 3 1 time. 3 goes into 21 7 times, and 3 into 27 9 times. Then you can ask yourself, is there anything else? Any other number that will go into those three evenly? And usually when you get to 1, I mean, always, not usually, always, you're done, right? Because 1 is prime. So there are no other factors besides 1 in itself. So we're done. The GCF is 3. 3 what? How many n's can we take out? So each of these, the most amount of n's that they all share is 2. It's funny because the greatest common variable factor is always the smallest number. Isn't that funny? Greatest and smallest. And that's because 2 is the smallest exponent value. That's because that's the greatest that they all share. So it's kind of funny. All right, now we're going to factor it out. So essentially you're dividing each of these by that GCF, right? So 3 over 3, that goes away, and we just have 2n squared, 2 n's. 21 over 3, that's the 7 that we found over here. And we have 1n, and then 9 that we found, and no n's. So we are done with factoring out that GCF. And then here, like if we were going to continue this problem, like if the problem said to solve, then we would keep going. We would see if we were able to factor this. If we weren't able to factor it, I'm going to show you guys even another method next week in class on something that will always work. So finding zeros of a polynomial. You may have seen this already in your OMHS lessons. There's a few ways to do that. Finding zeros is basically like solving. Solve the polynomial. Find the zeros. We have a few synonyms for this word zero. Here they are. Zero, root, and solution. So they all mean the same thing. You're trying to find the x value or the y value or the z value or whatever variable it is, and they all mean the same thing. So it kind of depends how the question is asked, and I just wanted to make sure you guys knew these are all synonyms for the same thing. And we have 3 different ways that we can find them. We can solve polynomials by taking square roots. We can solve them by factoring, and we can also solve them by graphing. So let me show you. A solution to a quadratic. So this says finding zeros. Remember, zero and solution are the same thing. So when we look at this graphically, I just wanted to show you guys what a solution is. So these are all examples of quadratics. The highest exponent value is a 2. And these are also called parabolas. You're going to see these a lot in Algebra 2. And here's the solution. I bet if we were together in live class, you would take your pointer tool and point at the solution. Here it is, there and there. This one, the red one, has 2 solutions. The blue one also has 2 solutions. And the green one has 2 solutions. So visually, what are solutions to a graph? It's where the graph crosses the x-axis. If you think about it, that makes so much sense because when we solve these, well, these specifically, we're getting x equals, x equals, x equals, and it equals those values. Here, this is 1, and x equals 2. There are 2 solutions. There are 2 roots. There are 2 zeros. They all mean the same thing. Here, x is -3 and 1, and here, x is -3 and 1.5, it looks like. Careful with these grid marks. This is 1. Let me see. This is -3. So this is -2.5. Excuse me. So the solutions are where the graph visually crosses the x-axis. And here, these are all x's. If it were, t or something, then this would be the t-axis. It's whatever that variable is. I just didn't want you to think it always had to be x. Like here's a. So to solve these, sometimes you're going to be able just to solve it sort of naturally. Remember, I'll say back in the day, we used to have these one-step equations, like solve for x, right? And you would subtract 1, and you would get x equals 4. Of course, they got more complicated. We saw things like this, solve for x. Here, we're doing the same thing, and we have talked about this already. If we have the a term is already by itself, but we do have to get rid of the squared. Do you guys remember the inverse of squaring? Or the opposite operation of squaring? And it is square rooting. I just made that a verb. I don't know if that's right. But it's taking the square root. So we can do this sort of inverse operation just like we do with addition and subtraction and multiplication and division. And we can just take the square root of both sides. Remember, when we're taking the square root, we're looking for pairs of things. So this a squared, remember, that's the same as a times a, right? So look, what is the square root of a times a? We found a pair. Remember, that was like the whole big deal when we did these. So the a comes out. That's why it works. That's why you get a by itself. Square rooting and squaring are inverses. So they essentially, I don't like to say cancel each other out because that's not really the mathematical term, but they kind of do. They cancel each other out. They're inverses. Let me get my pencil back. Okay, for some reason it says control. I want it to stop saying that. Hold on. My new pen and I are going to be friends. I promise. All right. So remember what happens when you take the square root of both sides? So what is the square root of 4? The square root of 4 is 2, right? But don't forget, we have to include the plus and the minus. There's a positive solution and a negative solution. And that's because 2 times 2 is 4. But also, negative 2 times negative 2 is 4. So that's why these quadratics have two solutions. Just like we saw, oh, it's not letting me. Just like we saw in those graphs cross the x-axis in two places. Sorry about that, you guys. I was trying. All right, sorry about that, you guys. I was trying to get my pen to work again. And we started off great. And now it has some issues, but hopefully we'll continue fine. All right, so let's try this one. The goal, again, is to get the variable by itself. So here we have a 2 with the x. So first we need to divide both sides by 2. And you'll get x squared equals 9. Now, if only I could figure out how to get rid of that little control symbol. Do you guys see that? I know you see that. Hopefully it's not too much of a distraction. I'll pretend like it isn't there. All right, so now we can take the square root of both sides, and you get x equals plus or minus 3. So again, that's going to cross the x-axis in two places, at -3 and +3. So here's some other examples. Don't forget that at any time you guys can stop this recording and try these on your own. So we're going to get the variable term by itself. Here we have to subtract 2 from both sides first and get k squared equals 25. And then just like before, we're going to take the square root of both sides and we get k equals plus or minus 5. All right, here we go. Square root, square root. You'll start to get into a rhythm. You get plus or minus the square root of 40. So 40 is not a perfect square, meaning, two numbers multiplied by themselves don't equal 40, but can we reduce it? Do you guys remember reducing radicals? We're basically going to break down 40, and you can do a factor tree if you want. 40 is 2 times 20. Remember doing this? And then 2 times 10, and then 2 times 5. So you kind of go down until you get all of those prime numbers, and then we're going to list them out. There are 3 2s and 1 5. So remember, we're looking for pairs of numbers. So it looks like we have one pair of 2s. So that means it's going to come out. So we're going to have plus or minus 2 root 10. Now, of course, you could get a decimal answer, but we do need to remember how to simplify these. So it's good practice. 2 times 5 is 10. All right, our last one, we'll take the square root of both sides. And you get x equals plus or minus the square root of 21. Now, you may already realize this, but when you factor tree 21, all you get is 3 times 7. So there are no pairs of numbers. Those are both prime. So really, we're just going to leave this one square root of 21 and call it a day. All right, so let's try this. It says solve, just like it said the other one. So you're like, okay, I'm going to solve this like I usually do. And maybe you think, oh, I'm going to subtract 10 from both sides. Let me do that over here. Because that's kind of the natural thing to think, right? You're like, okay, minus 10. But then look what happens. You end up with two terms with different exponentials there. So you can't combine these. We can't get x by itself naturally. But now we have a new tool that we can use to solve for x, and that's factoring. So whenever you do have three terms, and we're going to see mostly that they decrease from the power of 2, we're going to be factoring quadratics. We're going to factor these. Remember, the goal is to get it to look like that. And there are multiple methods out there. You may have heard or learned something called slide and divide. Maybe you're comfortable with guess and check. I know that the OMH lesson refers to guess and check, but I showed you guys factor by grouping because it always works. So I'm going to stick to that. I'm going to make myself a mod chart. Remember that mod chart we learned? Remember, we're looking for a number that multiplies to give us the first times the last. So 10x squared. And then we're looking for two numbers that add, that's the A, to give us the middle term, 7x. All right, so we're going to start listing our numbers. This is just a chart to help us organize things. So we're looking for two numbers that multiply together to give us 10x squared. So just start thinking, what times what is 10? Well, we could always have 1x times 10x, right? And then 2x times 5x. Those are the only two pairs of factors. But we want the pair of numbers that adds to give us 7x. Well, 1 plus 10, that's 11. So that doesn't work. Ooh, look, 2x plus 5x is 7x. So we found our pair of numbers. So once you find your pair of numbers, you replace the middle term. So instead of 7x, we're going to write 2x plus 5x. And see, I didn't change the value at all. 2x plus 5x is 7x. So all we did was sort of write it in a different way. And this is that step where we're basically going in reverse. Remember when we multiplied out polynomials? This is our sort of reverse method, if you will. All right, now that we have four terms, we're going to factor by grouping. So we look at the first two and say, what do they share? What is the GCF of the first two? It's x. So we're going to divide out or take out an x from each term. So there's an x left in the first term and just 2 in the second. Now, if we look at the second two, we can see that they share a 5 And you guys can always do the cake method off to the side over here if it helps you visually see. 5 is the factor that goes into each of these. And then we're going to divide each by 5, and we're left with x plus 2 equals 0. This is the first time we've seen equals 0 there. That's because we are going to solve. All right, here's that final step we've talked about, and this is why it works. So if you look, we technically have two big terms, right? Let me highlight these. We have this term, because it's connected by multiplication right there. And then we also have this term. Let me color the other one in. So if you guys were to think of these as two big terms, which they are because it's separated by that plus there in the middle, what would those two big terms share? What's the GCF of those two terms? Hopefully you're saying out loud to your computer screen, look, they each share that x plus 2. So we can essentially factor it out. So I know that I've said for a while now, this is sort of the magical step, and then I would tell you later why it works, and that's why it works. These are essentially two big terms, and that is the GCF. You can take the whole thing out. So I'm going to take the whole thing out. I'm going to put it over here because that's usually how we've written it. And then what's left? Well, what's left of each of them is just what's in front. So it's kind of the same idea of taking out a GCF. If you don't like to think of it that way, you can think of it as magical. Whatever your heart desires, and it equals 0. Okay, so I have a very important sort of big thinking question for you guys. Look at this. We have two things that are multiplied together to give us 0. This times this. Two big things. X plus 5 times x plus 2 equals 0. So when you multiply two things together and you get 0, what do you know about at least one of the things? What does one of those values have to be? Think about it. 2 times 0 is 0. 27 times 0 is 0. 0 times 132 is 0. What do you see about each of these math problems? At least one of them has to be 0. It's called the zero property of multiplication. When you multiply two things together and one of them is 0, you always get 0, right? We learned that back in the day. Anything times 0 is 0. So when you have something set up like this, we know one of them must be 0. And when I say one of them, I don't mean the x value. I mean the term, the whole thing. Remember, this is a whole number here. So because of that, because of the multiplication, the zero property of multiplication, I'm going to write that up here. Zero property of multiplication, we are allowed to do this. What we do is we set each of these equal to 0 because we know this term, at least one of these terms, the whole thing, that's why I'm circling it, has to be 0. So we're going to set them each equal to 0 and solve for x. So they become two little mini solving problems. So we'll subtract 5 from both sides. X equals -5 and x equals -2. Those are our two solutions, our two zeros. You guys remember the other word? Root. Solutions, zeros, roots. They all mean the same thing. Guess what? That's where this graph will cross the x-axis. So I'm not going to do it right now because I'm a little hesitant to, well, yeah, let's try it. X squared plus 7x plus 10. I was worried to change my screen because I didn't want my thing to mess up. I don't know what's going to happen to my face when I do this. So let's try. I'm going to open up Desmos, hopefully. Hey, I'm still there on the bottom of the screen. All right. Oh, I didn't mean to go there. Okay, so let's graph this quadratic. Remember, you can just type it in as you see it, and I wrote it down. So we have x squared plus 7x plus 0. Nope, it's not 0. Hold on. What was it? 10. Forgot the 1. Okay, there we go. Ooh, there they are. I say they because I'm talking about the solutions. So x equals -5 and x equals -2. And see, the y value is 0. That's why we were allowed to set it equal to 0. And you can do a happy dance. So some people at this point, they're like, wait a minute. Does that mean I can use the calculator to help me factor? Kind of, but not always and not really. So we do need to use that mod chart or whatever method you like. Sometimes it will help you, sometimes it won't. So we do need to know that chart method. But this is pretty cool. You can visually see the solutions or the roots that we get from factoring and solving. I think that's pretty cool. Let's try another one. Solve by factoring. So you can see this one looks a little bit different. The main difference here is, look, we have a -5 on the right-hand side. Well, in order to start solving, it must be equal to 0. I mean, you could certainly try to start solving this the natural, I say natural way, and we would probably subtract 19 from both sides. But then again, you would get stuck like we did the last time. You'd have a squared term and a z term, and you'd be like, what do I do now? So anytime you have a squared term, you're likely going to factor. Likely. You're either going to solve by taking the square root, or you're going to factor. So in order to factor, we need those 3 terms all on the same side. So let's get 5 over here with its buddy 19, those constant values, right? So we're going to have z squared minus 11z plus, what is this, 24, equals 0. Now we can factor. I'm going to make my ma chart. We're looking for a number that multiplies together to give us the first times the last. So 24 times z squared. And it's got to add to give us the middle term, -11z. So these are sort of our goals. So let's start listing out the numbers here under multiply. 2 numbers that give us 24. There's a lot. So maybe 1z and 24z. And then 2z and 12z. And you guys can definitely use your calculator to help you with this if you need to. 3z and 8z. What else? 4 works. See how I'm kind of systematically starting at 1 and going up. 4z and 6z. 5 doesn't work. 6 works, but I already have 6, right? 7 doesn't work. 8 works, but I have it here. 9 doesn't work. 10 doesn't work. 11 doesn't work. 12 works, and I have it here. So you can see we've got the full list now. So just pick the pair that gives us -11. Look at all of these. We see that they're all positive. So when you add them up, you'll never get a negative number. But don't forget that when you multiply 2 things together, you can also get, let's see, positive times a positive. That will give us, I think there might be an error in this problem. Let me double check. Let's figure this out together. So I'm going to write this down. And let's graph it and see. I may need to adjust the problem before we can solve it. Nope, we should be able to factor it. So 3, it crosses at 3 and 8. Okay, so here we go. A negative times a negative gives us the positive 24. So we have all these, it's basically a positive negative for all of these, right? Because a positive times a positive is a positive, and a negative times a negative is a positive. So this number has 8 different pairs you can use, plus minus. So when we look at these, we want to take this one. We want to take negative 3z minus 8z, because that's going to give us the negative 11. And do you guys see how I remember I said like you can use your graphing calculator to help you factor? We kind of just did. Did you see that? Like I graphed it and I saw that the solutions were negative or positive 3 and 8. And so we're going to talk about this later, but that will help you determine a factor. These are factors, not solutions right here. So let's replace the middle term. We have z squared minus 3z minus 8z plus 24. And now we get to start factoring by grouping. Group the first two and the second two. So the first two, they only share a z, so we'll take a z out. And we have left a z minus 3. The second two, be careful when there's a negative in front, you should always just take that. Put the negative, whatever sign is here, that's what's going to go down here. And you'll likely see that they share the 8. So we're going to divide each of these by negative 8. Right? It's a negative 8 that we took out. So negative 8 divided by negative 8, that's just the z. And then positive 24 divided by a negative 8 is a negative 3. Remember, you can always double check yourself. You can say, okay, negative 8 times z. And then negative 8 times negative 3 is a positive 24. And if you look, these match. So you know you did it right. So we would just take the 2 GCFs, z minus 8 and z minus 3. Now here comes that zero property of multiplication. You just set each of those equal to 0. Z minus 8 and z minus 3. So these are known as factors, right? Because two things multiplied together to give you something are factors, whatever it is. So these are the factors, but let's find the solutions. So we would add 8 to both sides. So z is 8 and z is 3. Just like we saw when we graphed it here in Desmos. 3 and 8. There it is. So see, you get those solutions once you end up solving. But to get the factors, we have to factor. So z minus 8 is one factor, and z minus 3 is the second factor, because they're being multiplied together. And that's why it's called factoring. So that's pretty cool. All right, let's keep going. So we're going to start to get into a routine. You guys are going to get used to seeing the types of questions that are asked and kind of know how to approach it. So you see this squared term and you're like, ooh, I probably need to factor this. So I'm going to get everything on the same side. So we have 6n squared minus 18n minus, what is that, 24? Yeah, equals 0. All right, then it's always a great idea, remember, to check to see if there's a GCF that you can take out of all 3 terms. And here they all share a 2. And I think, here, let's just do this. Let's do the cake. So we'll start with 2. So 2 goes into 6 3 times. 2 goes into 18 6 times. Nope, 9 times. Caught that fast. 2 goes into 24 12 times. Now let's keep going, right? Let's try 3. 3 goes into 3 once. 3 into 9 is 3. And 3 into 12 is 4. Cool. So we're done, right? Because we got down to 1. So our GCF is 2 times 3. So we're going to take a 6 out of everything. So we have n squared. And basically you have, well, the cake can help you. It's these numbers down here is what you end up with. That's pretty cool. So 18 divided by 6 is 3n. And 24 divided by 6 is 4. See, those coefficients match the last line of the cake, the last layer of the cake. And some of you might be wondering, like, why did we even have to do that? I mean, you don't have to, but it's going to make factoring a lot easier. Because once we now set to do our Ma chart, now look, we're only going to factor the inside piece. We're going to leave 6 alone for now. So the first times the last gives us negative 4n squared. Much smaller than whatever 6 times 24 is. And then the middle term is negative 3n. So let's list our factors of negative 4. That'd be a negative 1 times 4, negative 4 times 1. This is where there's a lot too when you can have either one being negative. What else? Negative 2 times 2. We don't really have to write that one twice, right? Because the 2's are the same. I mean, you know. I think that's it. So which 2 add to give us negative 3? And it is this one, and we can check it. Yep, negative 4 plus 1 is negative 3. So we found our pair of numbers. So I'm going to replace the middle term. N squared minus 4n plus 1, n. And let's factor by grouping. We're just going to kind of leave the 6 out here for now. We'll bring it down later. So the first 2 terms, they share an n. And we have n minus 4 left. And the second 2, they don't really share anything. And when they don't share anything, it's just a 1. So plus 1. And you can, if you need to, you can divide each of them by 1 and see you have just what you started with. All right, and these match. So our answer would be n plus 1 times n minus 4. Oops, I'm going to bring down the 6. It's all part of the answer. I just didn't want it to get too confusing there when we were factoring. So the multiplication property of 0 says we can set everything that's being multiplied together equal to 6. So we'd have equal to 0. 6 equals 0, n plus 1 equals 0, and n minus 4 equals 0. Does 6 equal 0? Nope. So that's kind of like an extraneous solution. And then we would subtract 1, n equals negative 1, and n equals 4, right? I'm going to write this problem down and take it to the calculator. Let's take it to the calculator, folks. And I'm actually going to put this one in exactly how it was given to show you can also do that. And let me do it properly. There we go. 6n squared. Why did it give me that slider? I don't want a slider. Okay, 6n squared. Oh, because it's n. That's cool. Okay, I wonder if that's going to mess us up. Like, maybe. Let's see. Maybe we'll have to just do x. Yep. You know, as smart as Desmos is, look at that. We only support implicit equations of x and y. Interesting. So, okay, we'll use x. I guess that's because they already have their axes set as x and y. All right. Minus 18x. Minus 18. Is that right? Did I copy that right? I have issues with copying things. You guys really realize that, right? 6n squared minus 18n minus 18 equals 6. Okay. All right. Here's our solutions. Negative 1 and 4. Woohoo! That's what we found. That's exciting. Okay, let's do another one. You guys are hanging in there with me. I know this is longer than the most recent play posits have been, but we are almost done. So this is when we're going to talk a little bit about solutions and factors. So here's a graph of this quadratic right here. And let's just practice factoring. So we're going to do a Ma chart. So first times the last, that is 2x squared. We want a number that multiplies to give us that and adds to give us negative 3x. Okay, the only factors that 2x squared have are 1 times 2. That's 2x squared. Thankfully, 1 plus 2 is 3, but we need a negative. So these actually will need to be negative. So it really does help, I think, to write these charts out and write what your goals are. So that way you get your signs right too. Negative 1x times negative 2x is a positive 2x. And negative plus negative gives us that negative 3. So we replace the middle term and factor by grouping. So we'll group the first two and group the second two. The first two, they only share an x. So we have x minus 1. The second two, remember, bring that negative down. Whatever's in front there, bring it down. And they share a 2. So we're dividing by negative 2. We have x minus 1. And I want you to be careful. I don't want you to always just write whatever you wrote here because it might be wrong. Like that's how we can also check ourselves. So make sure you're doing the math over here in the second set and not just like writing it. So positive 2 divided by negative 2 gives us that negative 1. Okay, so we have x minus 2 and x minus 1. Now this doesn't have equal to 0, but we can add it if we wanted to solve. So remember that multiplication property of 0 says we can set each of these things, these terms, these factors equal to 0. And we get two little solving problems of x equals 1 and x equals 2. And here it is graphically. See, this is going by 2's. So here's 1, x equals 1 and x equals 2. So the thing I wanted to point out here, though, is the difference between a factor and a solution. So again, I squared these. I talk about this so much every year. It's really interesting, and the graph can be helpful. I just don't want you guys to confuse factors and solutions. So I don't want you to get this problem, graph it, and say, oh, it's 1 and 2. So I'm going to write x plus 1 times x plus 2. See how that's not the answer? See how the signs are wrong? And that's a common mistake, so I want to like talk about it a lot. And we'll talk about it more when I see you guys. So the graph can help you, but it's not going to give you the factored form. It's going to give you the solutions. So you can kind of work backwards if you want to. You know, the solutions are from the graph. You're like, ooh, I see it crosses at x equals 1, and I see it crosses at x equals 2. Cool. So I know in my head that means those are the solutions here. So you kind of have to work yourself backwards and say, oh, so that means x equals 2. Then let me get 0 on the right-hand side. So I would subtract 2. You're kind of working backwards. And see, then you get x minus 2. Then you get the factor. So there's a difference between factor and solution. Remember, factors of numbers are things you multiply together. Like this, x minus 2 is one factor and x minus 1 is another. We're not used to seeing variables in factors. We're used to seeing like, 1 times 2 and 2 times 3 and whatever, numbers. But now we're seeing variables. This whole thing right here is a factor. So let's look at this one. The solutions are 1 and negative 3. X equals negative 3 and x equals 1. Those are the solutions. So if I wanted the graph to help me factor, I could kind of work backwards and say, oh, that must mean the factors are x plus 3 and x minus 1. See that? And you could check yourself, set these be equal to 0, and you would get -3 and 1. But it's also a good idea to multiply this out because it's not always going to work. Remember this example? Where'd it go? Where'd it go? This one, where we had this extraneous 6. Remember that? It would not have worked here. And then that's because we have a number larger than 1 in front of the leading coefficient. So my whole sort of point in this whole, like, however many minutes I've been talking about this is, yes, you can use your calculator to help you with the graph, but I don't want you to rely on it. You guys do need to learn how to factor, because using where it crosses the x-axis to factor is not always going to work. Like I said, it would not have worked in that one where we took that 6 out first. So I don't want you to use it to factor. I want you to use it to help you confirm your solutions. We can't use it to factor. I hope that makes sense, and hopefully it will the more we do this. So I will see you. I've missed you so much this week, you have no idea. I mean, you might think, oh, teachers are getting like a big break and a vacation. But you guys, I'm a teacher because I like to teach you. I like to interact with you. And so I've been kind of sad this week. I mean, a vacation week is different. You know, everybody's on vacation. Everybody's gone. Spring break, winter break, whatever. But you guys are schooling. And I'm like, I want to see my kids. So it's been a little sad, but I hope that you guys are having a great week and that if you're 8th grade, that your testing has gone well. And just don't forget that I realize that the OMHS work now is a little ahead of where we are. So if you have had to wait to take that test, that's totally fine. Remember, that's the beauty of our program. So if you are waiting to take your Unit 2 test until next week, totally fine. All right, you guys, I will see you on Tuesday. Bye, everybody.